Hello, welcome to this virtual event where we will introduce the engineering discipline of functional safety, specifically in the context of new product development. FMEDA frequently gets a message from an engineering manager saying something like, "Our marketing department wants a SIL certification." And what is that? Can you help? And we will answer yes. And in fact, we can do some of that hopefully today. My name is Bill Goebel. I've been fully involved in functional safety for several decades and have enjoyed helping to advance the engineering methods. I work for a company called FMEDA. FMEDA is a company that specializes in automation systems, alarm management, cybersecurity, and functional safety. FMEDA has a suite of products and services to help all those who are new to functional safety, from training through functional safety certification. For some, the discipline of functional safety seems overwhelming. I once asked a senior engineer, George, for an estimate of the effort it would take to meet this new functional safety standard. He said, "Give me a week." I said, "Okay." I went back a week later and asked, "Well, what's the effort?" He looked me straight in the eye and said, "If we take all the engineers in this building and work the rest of our lives, we will not meet this standard." Oh boy, George, bit of an overreaction? Well, for those who have only a little bit of that panic about functional safety, we can explain a bit today. We can talk about what is functional safety. We can categorize many pages of requirements into two fundamental concepts of functional safety. We can present an example new product development which meets the requirements. And we can discuss functional safety certification, what it is, and how to prepare. Functional safety is an engineering discipline defined by international standards for the design and operation of automatic protection systems. You're probably thinking, what's an automatic protection system? Well, it's a system that detects hazardous, dangerous conditions and automatically takes action to reduce or hopefully eliminate the harm. The goal of functional safety is pretty simple. Number one, we'd like the product to work. Every engineer wants their products to work. We want this product to work correctly and be very reliable. But for functional safety, we must go further. We must deal with product failure modes and design so that if the product does fail, it will fail to a safe state. Functional safety is spreading to many different industries. You can look at the various potential applications from different industries. And let's take a look at the autonomous lawnmower, for example. One of the most important safety functions is detect an obstacle. A person, maybe an animal like my pet, maybe a rock, which could damage equipment. When we detect this hazardous condition, we will de-energize the wheel motor, de-energize the brake withhold, which will apply the brake, and notify the operator via a wireless, probably cell phone connection. And if we look at all the other applications, we are seeing common requirements for detecting dangerous, hazardous conditions and taking actions. Let me drop down to petrochemical. Petrochemical applications are where functional safety started. For example, detect high level of fuel and close an inlet valve to prevent further filling, actually to prevent tank overflow. Note the common theme: reduce energy to achieve safety. IEC 61508 is the basic safety standard from IEC. There are industry-specific standards derived from 61508, and these standards provide different industry vocabulary and deal with different safety priorities of different industries. 61508 is used, however, in many industries where there is no industry-specific standard. You can read the definition from IEC 61508. I remember reading it early on and thinking, I'm not sure I understand this. First thing I did is look up the acronym EUC, Equipment Under Control. And I was thinking, now what does that mean? It's the process we are trying to protect. FMEDA is not very formal, so we prefer a definition. Functional safety is a structured methodology for managing risk by defining engineering processes, including essential product design requirements, and performing probabilistic design analysis. We can take all of the pages of requirements and sum them up into two fundamental concepts. Number one, on the left, is the safety life cycle. That's the term they use for a detailed engineering process created to achieve high levels of design quality. The other concept, probabilistic performance-based system design, deals with random failures. That helps us achieve higher levels of hardware reliability. These categories of failures are called systematic failures, design documentation mistakes, random failures like hardware component failures, or maintenance failures that cause hardware failures. An engineering process for new product development must be documented. Now, you probably recognize the V model on the right-hand side. It's very commonly known. The safety life cycle applies from initial requirements to the release to production. There is a metric called systematic capability. The development process is rated per process rigor and design features. A defined development process is assessed and given a rating according to one of the 4 levels in the standard called Safety Integrity Levels, or SIL. Systematic capability rating just matches the safety integrity level. As the level number goes up from 1 to 4, the level of process rigor and design features increases. The probabilistic concept depends on detailed hardware analysis. Again, there are 4 safety integrity levels, and you will notice that each level has a maximum probability of average dangerous failure. The development process for systems versus product is quite different. Looking at a system for a minute, consider the example of a low-speed vehicle such as an autonomous tractor. Sensors are selected to recognize and sense the dangerous conditions. For example, a LiDAR might be used for obstacle detection. A controller, typically an embedded controller, is part of the system because it's programmed how to detect signals from these various sensors and convert them to potentially dangerous, recognizable conditions. And finally, there are products on the output of the safety controller, which are used to actually implement the safety function, and in most cases that means removing energy from the process. Each safety function is assigned a SIL level based on application risk. As we look at different applications in different industries, we see that most risk analysis shows a SIL 2 or a SIL 3 requirement. Product development is quite different. If you look at the bottom part of the screen, what we're talking about here are devices, products like the sensors, like the safety controller, and like a flashing light or a motor shutdown relay. Devices are products chosen for use in an automatic protection system, and they are typically certified for functional safety by an accredited certification body. Now, we talked about the need for a development process at the product level, and we showed you this V model, but that is not nearly enough detail. A documented development process for functional safety must show the engineering tasks, input documents for each task, output documents produced by each task, and the design verification tools. Let's call them quality verification tasks that check to make sure each step was done properly with sufficient quality. A documented, audited process is required with sufficient detail for a new engineer to understand. The concept of corporate tribal knowledge is not sufficient. Now, here's a drawing that shows a development process with more detail, including the design verification tasks. We're going to talk about each phase of development from this picture in the next few slides. Product requirements include market requirements, regulatory requirements, and functional safety requirements from a hazard and risk analysis if the product is being designed for a specific application. However, that's not typically the case, and for general purpose products created to be sold into many different applications, systematic capability requirements are market-driven. Generally, requirements are categorized. They might include, for example, system safety assumptions. They might include safety integrity requirements, safety function requirements, to as much detail as necessary for proper implementation. As soon as draft requirements are available, we must start the validation test plan. At this point, it's perfectly acceptable to simply write down high-level test objectives. And what we mean by the word test is any actual test, an analysis, or an inspection. Every requirement must have one or more tests. Each test could satisfy one or more requirements. We start the validation test plan because we need to make sure that all requirements are testable. If we can't think of at least of a validation test plan objective, then that requirement is probably quite unclear and must be rewritten. One thing that is required by functional safety, and although it seems bureaucratic at times, it's really valuable. There must be links between requirements and test objectives. What we do with this is verify that there are at least one or more tests for each requirement. Now, fortunately, most requirements editor tools include this capability. Once we have requirements, we can start architecture design. We create and review an overall design by hierarchically partitioning large functions into subfunctions, and that's a classical structured engineering process. We go down to the level where each functional unit has one function or a related set of functions. When that is done, functions are allocated to hardware and to software. When we have a good hardware and a good software architecture, we perform design verification with design deviation and mitigation analysis to verify design integrity. We update the requirements, perhaps if we find things we have missed, and then we must update the validation test plan. What is this thing called design deviation and mitigation analysis? Well, it is an enhanced DFMEA technique, design failure modes and effect analysis. DDMA accomplishes the essential purposes of DFMEA, but it also gathers the important information needed to document functional safety and to provide input to later analysis tasks. The primary value in a DFMEA is to find problems early in a design, and if needed, recommend mitigations. In other words, this is not good. How do we fix this problem? Don't we do this in a DFMEA? Yes, the essential purposes is accomplished. But what's missing is the need to gather important information needed for functional safety and provide input to later analysis, because that's not normally part of a DFMEA. The information we need includes a description of all automatic diagnostic mitigations intended for the design. We need to know the action taken when a diagnostic detects a failure mode. Yes, you have to address that in the architecture design. We need to estimate the expected effectiveness of any diagnostic for a particular deviation, a particular unit failure mode. We also should, at this point, define any latent fault tests, or what's known as a proof test. A proof test is a valuable concept that can drastically improve safety. It needs to be planned as part of the architecture design. And lastly, during the architecture design, we understand how units are connected. This is the perfect time to define any needed integration tests. Now, it's not commonly done in DFMEA at all, and a lot of people say, why do you do that for? I'm not going to run my integration tests until later in the process. And the answer is, we understand the architecture now. The last thing we want to do is forget what it is when we're out of context and have to go back and spend time duplicating effort to really understand architecture again. The best time to get all this information is during the architecture design review, or in other words, during a DDMA. There are DDMA tools available. Some of them have suggested deviations and mitigations. Some of them provide a common resulting impact, an end-level failure mode. Some of them have suggested integration test objectives and latent fault test objectives. Some of them have estimates of the diagnostic coverage for designated automatic diagnostics. Let's take an example of this simple visual flasher. Whenever a dangerous condition occurs, an input signal tells it to start flashing a bright red signal. Normally that means, if you're near me, leave now. The power supply block is of interest. Let's go to that first because it's something most people understand. If I hit a DDMA tool and select a unit power supply, the tool will provide failure modes, or what we call deviations, and they are given in this light blue background color. I can see that the designers have chosen 3 mitigations for these particular failure modes, and they are all displayed from a suggested list. When the architecture is complete, and we have a list of all the blocks, and we have a description of the function of each block, we can proceed with hardware design. And that's, of course, where you choose components, you do an electronic circuit design, and a schematic showing the relationship between the components, and basically describe how they meet the intended functionality. When that's all done, when the draft detail hardware design is done, we can perform a task called FMEDA, Failure Mode Effect and Diagnostic Analysis. Finally, of course, we build the hardware prototypes, and often we will do what's called a fault injection test as an integration test at some point later in the process. Now, I talked about early on the second fundamental concept, probabilistic performance-based system design. That is done in the FMEDA. What's an FMEDA? It's a bottom-up inductive quantitative analysis where failure rates and failure modes of each component are used to predict the failure rates and failure modes of a subsystem. Subsystem blocks can then be used to predict the failure rates and failure mode of the next higher level architecture blocks, all the way up to the complete device. An FMEDA does need a quantitative failure rate database for each component as a function of product environmental stress, and actually of design strength. Automatic diagnostics mitigations will classify these failures into detected or undetected, and latent fault proof test effectiveness can also be predicted in an FMEDA. Well, why do we do this thing called an FMEDA? It sounds complicated. Well, it can be if you don't, especially if you're using a spreadsheet or you're doing it the old-fashioned way. But this is not just a checkbox for functional safety certification. There are many reasons the output of an FMEDA is needed. It's needed for design improvement. An FMEDA often identifies weaknesses in a design right now before you even build the first prototype. The FMEDA will predict field reliability performance, which is useful in certain business metrics. An FMEDA will provide customer assurance. The failure rates and useful life of every device are considered as part of the systems level probability of dangerous failure calculation. And lastly, the FMEDA is an essential part of functional safety certification evidence. There are FMEDA tools on the market. A mechanical and electrical component database is absolutely required. The component node editor screen from FMEDAX is shown. In this case, we enter all the components into the unit tree diagram. For each component, we will map the component failure mode to the unit failure mode, and then we can answer questions about design strength for each component. And when all components are entered, you click the tab to get the results. Component entry can be a pain. Bill of material import does help that quite a bit, but you still have to make sure all the components get entered properly. The FMEDA output is a set of failure rates in different failure modes, categorized by detected versus undetected. Another output is the useful life of the device, because that defines the period of time for which the failure rates are valid. A third important output is your latent fault or proof test coverage or effectiveness. FMEDA can produce all of that information. System analysis provides the metrics we need to see if this particular design meets SIL requirements. An FMEDA tool should provide all of the various failure rates for all of the various failure modes. It should provide a diagnostic test interval. How fast do the diagnostics work, which is important when considering demand rates. It should provide useful life. That's the period of time when the failure rates are valid. Software design and implementation can proceed once the software architecture is created. Normally that involves adding any additional design detail as needed. We need to code all the modules. We need to perform static source code analysis and unit testing. When the hardware and the software is done, integration testing begins. For hardware-only integration, we look at the different blocks and make sure the electrical signals or mechanical interconnections provide what's necessary to make sure all the pieces of the puzzle fit together. Same with software integration. Does the output of one software unit provide what's needed? The objective is pretty simple. We've got to make sure all the pieces of our design fit together properly. Integration test plans should be written to confirm behavior in normal operation and confirm that the design behaves or fails as expected during abnormal operation. Most integration test objectives are defined during the architecture design review. Given that list of test objectives, the test plans are then completed and detailed with the test environment, persons responsible, versions under test, specific pass-fail criteria, any test equipment needed, calibration details, and so forth. Results are often recorded right on the test plan, no reason for extra documentation. If something fails, we need to write up an action item so that the failure mechanism can be reviewed and resolved as required. When a product is fully integrated and we effectively have a prototype, we can start validation testing. Validation testing is considered a black box test, and of course, the validation test plan is based on the validation test objectives that we defined during the requirements phase of the project. Why? Hold it. Why do we need all this documentation? Well, the objective of all this is to make sure we have enough so that the original design intent is clearly specified, so that we can make changes in the future without creating more problems than we fix. I know that sounds sarcastic, but boy, that happens a lot. This list looks bad because it's a long one, but remember that a lot of the documents can be created by the design tool. What is functional safety certification? Well, it's a process by which a system, a product, a process, or a component is evaluated per IEC 61508 and one of the industry-specific functional safety standards. This certification process is governed by another standard, IEC 17065, which dictates the requirements of how to operate a certification program. Who gets to do certification? Well, technically anybody could, but there are accreditation bodies that will audit and accredit a certification body. For example, Exida.com LLC is accredited by ANAB, the ANSI National Accreditation Board, and Exida Ireland Limited is accredited per INAB, the Irish National Accreditation Board, because the EU has set up its own system of accreditation. How does a product get a functional safety certification? Well, at this point in time, over the last decade plus, many others, maybe 100 companies have achieved a Systematic Capability 3 rating by Exida certification per IEC 61508 and other functional safety standards. They achieved this by establishing hardware and software development processes that meet the specific requirements of 61508 for SIL 3. They documented an architecture which meets SIL 3 requirements, complete with a DDMA analysis. They demonstrated good documentation and test results proving that they are actually following their process. An FMEDA analysis has been done with extensive fault injection testing and, if practical, verification via a field failure study. And lastly, they've created user documentation explaining how to use this product safely, typically called the safety manual. In summary, functional safety is a set of rules and methods for specification, design, and operation of safety functions, which are part of automatic protection systems. The goal of functional safety is to make sure everything works, has the highest levels of reliability practical, or that the system will fail in a safe, predictable manner. And although the engineering process looks tough, new methods developed in the last few years, including DDMA, and new tools are helping new product development achieve better results and balancing the trade-offs. Get ready with your questions. FMEDA does have a strong repertoire of resources for anyone who's new to functional safety, including webinars, white papers, blogs, training courses, document templates in Word, functional safety analysis services, and development tools, particularly the OEMX suite of tools.